Good morning. Welcome to the math department at Amjad High School. This is grade GS. For today's session, we'll discuss an activity. We will talk about the variations of a sequence. We will talk about bounded sequences, and we will talk about convergence of a sequence. Let's start with an activity. Consider the sequence UN defined by UN equals 1 over N, where N is an N star, which means N starts with 1, 2, 3, and so on. The question here is calculate U1, U2, U3, U4, and U5 and plot them on a real line. For sure, this question is quite easy, but we need to notice a pattern about the terms of the sequence. For N equals 1, you simply replace and you will get U1, 1. So if you want to replace the value of this sequence on a real line, so it's nothing but 1. So here is U1. Similarly for U2, it's half, so it's there. Similarly for U3, it's 1 over 3, and its position on the real line is here. So as you notice, U1, U2, U3. Now U4 is 1 over 4. U5 is 1 over 5. So these are the first 5 terms of the sequence. For this question and also for the question that will come next, you are going to answer 3 questions, and these questions we will answer them informally. We are just noticing or conjecturing a pattern about the sequence. These are the 3 important questions that we will talk about today. First, what do you conjecture concerning the variation of the sequence? Do you think that the values of the sequence are increasing or decreasing? For sure, if you notice here, U1 starting with 1, then half, then 1/3, then 1/4, then 1/5. Clearly, the values of the sequence are decreasing. For sure, this is not the formal proof that the sequence is decreasing, but as a conjecture, the values of the sequence are decreasing. What about the next question? Do you think that the values of the sequence, when I say the values, I don't mean only these 5 values, I mean all the values of the sequence. Do you think that the values of the sequence UN can be bounded by 2 real numbers? Can you name 2 real numbers where all the values, not only these 5 values, will be between these 2 real numbers? What if a student answers me and telling me that these 2, all the values of the sequence are bounded between, let's say, -1 and 1? I think that the answer will be correct, because if you keep on finding values of the sequence like 1 over 5, 1 over 6, 1 over 7, all the values on the real line will be inside the interval -1 and 1. Some other students may tell me, why don't you say all the values are between 0 and 1? That's also correct. But what about if a student is telling me that all the values are between half and 1? This is incorrect, because some values will be outside this interval. So this sequence is said to be bounded between 2 real values, 0 and 1, -1 and 1, 0 and 10, I don't care. What you need to do is to find 2 values. Remember that we are conjecturing, we're not proving, we're just noticing that the pattern says so. Now, do you think that as n increases, that the values of the sequence UN are approaching a certain value? What if we keep on finding the values? Notice here, U1 is here, U2, U3, U4, U5. If you keep on by finding 1 over 6, 1 over 7, 1 over 8, 1 over million, 1 over 10 million, if you keep on plotting the values of the sequence, it's clear that the values are approaching 0. This has to do with the limit concept. We can say informally for now that this sequence has its limit 0, which means as n tends to infinity, the values of the sequence are approaching 0. Let's consider another sequence. Consider the sequence un defined by un equals -1 to the n over n squared plus 1, where n is in n, which means that the first term starts with n equals 0. Calculate u0, u1, u2, u3, and u4 and plot them on a real line. For n equals 0, the first term is 1. Let me plot this term on the real line. It's here. So the next term, u1, is -half. Here is -half. Let me plot the next term, u2, which is 1 over 5. Let me plot u3, which is -1 over 10. Now, what about the fifth term, u4? It's 1 over 17. I'm going to repeat the same 3 questions for this sequence. So notice u0 is here, u1 is here, u2 is here, u3 is here, u4 is here. What if we keep on plotting consecutive terms? Are the values of un increasing or decreasing? Actually, the values of un are neither increasing nor decreasing. They are alternating between positive and negative, positive and negative. So this sequence is not monotonic. Do you think that the values, when I say the values, so I mean all the values, do you think that all the values of the sequence can be bounded between 2 real values? Actually, we started with u0 here at 1, then we moved to u1, which is -half. Then we will be moving inside and plotting more and more terms. Actually, we can conjecture that all the values will be bounded between -half and 1. If some other students are telling me the values are bounded between, let's say, -10 and 10, I will accept. I don't care about finding the least bounds. 30 question, do you think that as n increases, un approaches a certain value? What if we keep on plotting u0, u1, u2, u3, u4, u5 will be -1 over 26. You will be getting closer and closer to 0, but you will not touch 0. There is no term whose value will be exactly 0. But it seems, and I'm saying here it seems, because we're not proving formally, it seems that the terms of the sequence are approaching a value which is 0, as if we're saying that the limit of un as n tends to infinity is 0. Consider now the sequence un equals -1 to the n. The same question, plot these 5 terms on the real line. It's easy here. For n equals 0, u0 is 1. Here, u0 is. Now, for n equals 1, u1 is -1. Again, u2 will be 1. u3 will be a -1. And u4 will be also 1, and so on. If we keep on finding the terms, they will alternate 1 minus 1, 1 minus 1. The values are repeating themselves. This is what we call a periodic sequence, a sequence that repeats itself. Here it's repeating itself each 2 steps. -1, 1, -1, 1. The same questions. Are the values increasing or decreasing? I should expect an answer, which is the sequence is neither increasing nor decreasing because it's changing variation. Sometimes it increases to positive, sometimes it decreases to negative. Do you think that the values of the sequence un can be bounded between 2 real values? Clearly here, all the values of the sequence can be put in the interval -1, 1 closed. Again, some other students may say, why not between -2 and 2? It's okay. But I mean, I can find 2 real numbers where all the values are inside this interval. Do you think that as n increases, un are approaching a certain value? Actually, the values are grouping, sometimes at -1 and sometimes at -1. So they are alternating between -1 and 1. They are not approaching one real number. Actually, if I want to relate this to limit, and we will define this formally, in few slides. This sequence has no limit. This sequence is not convergent. We will define the word convergent in a while. One more example. Consider the sequence un defined by un equals n squared. Same questions. Let me start by plotting the terms. U0 is 0. U1 is 1. U2 is 4. U3 is 9. U4 is 16. What do you think about the three questions? Are the values of the sequence increasing or decreasing? Clearly, the terms of the sequence are increasing. This is an increasing sequence. So a sequence is said to be increasing if each next value is greater than the previous one. Do you think that the values of the sequence can be bounded between two real values? Actually, you can find what we call a lower bound. No values are less than 0, but you cannot put an upper bound. If you say 1 million, at certain level, the sequence will cross this 1 million. So this sequence cannot be bounded above. It can be bounded below by 0. So as one statement, this sequence is not bounded. A sequence is said to be bounded if you can find two real numbers where all the values are in between. Do you think that as n increases, un is approaching a certain value? Actually, if we keep on plotting the terms, so the answer will be clearly no. This sequence is divergent to infinity. So now let me give some formal definition. A sequence un is said to be increasing if and only if un plus 1 minus un is positive for all n. This is equivalent to say any term un plus 1 is greater than the previous term un. So if this condition is true, then the sequence is said to be increasing. Similarly, the sequence will be decreasing if un plus 1 minus un is negative. That is, each term un plus 1 is less than the previous term un. If un plus 1 minus un is 0 for all n, which means any term is equal to the previous term, then the sequence is said to be a constant sequence. Example, let me go back to the first example that we've started with. Consider the sequence un defined by un equals 1 over n. If the question is show that un is decreasing, we saw that the terms, when we plotted them on the axis, we conjectured, we said that it seems that the sequence is decreasing, but that was not a formal proof. If I want to prove it formally, I need to study the sign of un plus 1 minus un. So I find un plus 1 by plugging in n plus 1 in n here. So it's 1 over n plus 1 minus 1 over n. Now let me study the sign of this expression. Do not forget that n is a non-zero natural number here, which means that this expression is negative. Consequently, the sequence is decreasing. So this is how we prove formally that a sequence is decreasing. Now, let me define formally what a bounded sequence is. A sequence un is said to be bounded from below by a real number m if all the terms are larger or equal to this small m. A sequence un is said to be bounded from above or simply bounded above by a real number capital M if all the terms are less than or equal this real number m, not infinity, real number m. In general, a sequence un is said to be bounded if there exist two real numbers, small m and capital M, where all the terms un are found between this m and that capital M. This small m is called the lower bound of the sequence. This capital M is called the upper bound. Example, consider the sequence un defined by un equals 1 over n. Prove that 1 is an upper bound. To prove that 1 is an upper bound, actually we need to prove that all the terms are less than 1. How can we do this? We find un minus 1. It should be negative. un minus 1 is 1 over n minus 1 equals 1 minus n over n. Do not forget that n is 1 or more, which means that the denominator is positive, whereas the numerator is less than or equal to 0. So all in all, un minus 1 is less than 0. Consequently, un is less than 1, and 1 is an upper bound. Or un is bounded above by 1. So 1 is an upper bound. Show that un is bounded between 0 and 1. We have already proven that un is less than 1. All what we need to do here is to prove that un is larger or equal to 0. un is simply 1 over n, which is clearly positive since n is positive. So done. Actually, to prove that a sequence is bounded between two real numbers, it could be an easy exercise as exactly as this one, simply because in this example, the sequence, as you can notice here, is what is an explicit sequence. un is defined in terms of n, whereas if the sequence is a recursive sequence, sometimes it's not that easy to prove. We may use mathematical induction or whatever. So, but the formula is the same. To prove that a sequence is bounded above by m, it's enough to prove that un minus m is negative. So 1 is an upper bound, 0 is a lower bound. What do we mean by a convergent sequence? A sequence un is said to be convergent to a real number L if and only if the limit of the sequence as n tends to infinity, and don't forget here that n is a natural number. Even if n is going to plus infinity, n could be even, could be odd, because n is not a real number. N, not real in general. In specific, it's what? Natural number. But the question is how we find limit of a sequence. If the sequence is explicit, we simply find the limit as if we are finding the limit of a real function. If this limit does not exist, if it's infinity or does not exist or whatever, we say that the sequence is divergent. Which of the following sequences is convergent? First sequence, second sequence, third sequence. By the way, we conjectured that this sequence is convergent to 0 because when we plotted the terms, it seems that they all are approaching 0. Whereas this sequence, we said in the activity, it seems, but we said it seems. Now we're going to prove it formally. If we find the limit of the sequence O1 over n as n tends to infinity, this is an explicit sequence. It's very easy to find the limit as if we're finding the limit of a function. It's 1 over infinity, which is 0. This means that as n increases, the terms are convergent to 0, and the sequence is convergent to 0. What about the second sequence? The limit of un as n tends to infinity. It's infinity squared, which is what? Infinity, which means that the sequence is not convergent. Correspondingly, it's a divergent sequence. What about this limit? Limit of un as n tends to infinity is the limit of minus 1 to the n as n tends to infinity. The limit of minus 1 to the n as n tends to infinity. You have to consider two cases. Actually, whenever you are studying the limit of a sequence, sometimes it's critical to consider two cases where n is even or n is odd. In the previous two parts, it wasn't significant to consider two cases because in the two cases, the answer is the same. Whereas here, even if n is going to infinity, it's either even or odd because it's natural number. But here it makes difference. So un is divergent because if n is even, the limit will be 1. Otherwise, it will be minus 1. So the limit of the previous sequence does not exist. To deal with sequences, especially with recursive sequences, we need some theorems. These two theorems are so important and so practical. Any increasing sequence which is also bounded above must be convergent. So this is a theorem. If a sequence is increasing and bounded above, then it must be convergent. I'm not saying that the converse is true. If a sequence is convergent, it doesn't mean it must be monotonic. You can refer to the previous examples in the activity where we considered -1 to the n over n squared plus 1. It was convergent, but it was changing variation. Also, a decreasing sequence, which is bounded from below, must also be convergent. So if the sequence, if it happened that the sequence is decreasing and also bounded below, you can deduce directly that the sequence must be convergent. We are taking these theorems without the proof, but these are theorems that may be proven. To study the limit of sequences, also we need to study some properties as these two important properties. If un and vn have limits, and they are such that the sequence un is always less than the sequence vn, which means u1 is less than v1, u2 is less than v2, then the limit of un must be the limit less than the limit of vn. So the relation between the limits, if they exist, will be exactly as the relation between the sequences. By the way, this theorem holds true also for functions. If you have a function f of x, which is less than g of x for all x, and if the limits exist, then the limit of f of x must be less than the limit of g of x. Now, this is very important property. Actually, it's called the squeeze theorem. It's saying that if un, vn, and wn have limits, and they are as such, vn is squeezed between un and wn for n. And if, moreover, if the limit of un and the limit of wn, if the limit of un and the limit of wn are both equal to a real number L, then the limit of vn will be equal to that limit. For sure, this is always true, but what is more important is this. In case you have vn squeezed between two sequences, un and wn, and if, moreover, the limit of un and the limit of wn, the extremities, are both equal to L, then the limit of vn must also be equal to L. This is called the squeeze theorem. Applications: consider the sequence un defined by un equals to n minus 1 over n, where n is n and star. First question, show that the sequence is increasing. To prove that the sequence is increasing, but notice here that this sequence is explicit, you should expect easy questions or easy ways to answer. un plus 1 minus un, it's this minus that. Simplifying the expression, it's 1 over n times n plus 1, an expression which is clearly positive, which means that the sequence is increasing. Prove that 2 is an upper bound. To prove that 2 is an upper bound, we need to prove that all the terms un are less than 2. So let's find un minus 2 and prove it negative. un minus 2 is 2n minus 1 over n minus 2. Simplifying this is minus 1 over n, an expression which is clearly negative, which means that un less than 2, hence 2 is an upper bound of un. I can ask you this question here. Deduce that the sequence un is convergent. Since the sequence, to deduce, it means you need to use the previous two parts. Actually, to prove that the sequence is convergent, it's enough to go and find directly its limit, and its limit here is easy, but I'm asking you to deduce. To deduce that the sequence is convergent and to use the previous two parts, you need to use the previous theorem we have talked about, which is, since the sequence is increasing and bounded above by 2, then it must be convergent to element L. By the way, since the sequence is increasing and bounded above by 2, the limit must be lying between two values. The first term, where it has started and increased, and the upper limit. So the limit must be included between u0, or u1 actually, and 2, or equal. Calculate the limit. To calculate the limit, we can calculate the limit of this sequence directly because it's explicit sequence. Exactly as we find the limit of a function, this limit is clearly 2, and consequently this sequence is convergent to 2. Let me consider now a recursive sequence. Consider the sequence un defined by u0 equals 9, un plus 1 equal 8, un minus 6 over un plus 1. Prove that un is bounded below by 6. Actually, it's not that easy here to find un minus 6, because un, you don't have an expression, an explicit expression in terms of n. Actually, we need to do these by induction. For n equals 0, u0 is 9, a quantity which is greater than 6. So this statement holds true for n equals 0. Assume now that un is larger than 6 for certain value of n. To finish the problem, we need to prove that un plus 1 is also greater than 6. So we need to prove that un plus 1 minus 6 is positive. un plus 1 minus 6 is 8 un minus 6 over un plus 1 minus 6. Simplifying this and taking 2 as common denominator. As you can notice here, the denominator is positive because I know that un is larger than 6. We have already assumed this. Numerator, what about the numerator? Numerator is 2, which is positive, times un minus 6. But un minus 6 is also assumed positive. So all of this expression is positive, and consequently un plus 1 is larger than 6. Hence, un is bounded above by 6, proven by mathematical induction. Next part, prove that un is decreasing. To prove that un is decreasing, we need to find un plus 1 minus un. And that's 8 un minus 6 over un plus 1 minus n. Simplifying the expressions, this will be minus un squared plus 7 un minus 6 over un plus 1. You have to convince me that this expression is what? Negative, because I'm proving that the sequence is decreasing. How can we do this? Factoring the numerator, you will get minus into un minus 6 into un minus 6 over, this is un minus 1 by the way, over un plus 1. What about the sign of each of these factors? Un plus 1 is positive because un is larger than 6. Un minus 6 is also positive. And un minus 1 is also positive because un, do not forget, is proven larger than 6. So all of these three terms, three factors are positive. But you have a minus here. So this is positive, this is positive, this is positive, but the minus is negative. So all in all, it's what? Negative, and the sequence is clearly a decreasing sequence. Now, the question is, deduce that un is convergent and calculate its length. Since the sequence is decreasing, it started with 9 and decreasing, but it's bounded below by 6. So by the previous theorem, this sequence must be convergent to a limit L, and the limit L should be between these two values, 9 and 6, with the possibility to be equal to one of them, because it started with 9 and it's not going to go below 6. So it has to converge in between. So since un is decreasing and bounded below by 6, then un is convergent to a limit L. Do not forget it. It's very important to write the condition on L. You will see why. L has to be between the first term and the lower bound. Now, how to calculate the limit? Actually, this is a recursive sequence. You cannot calculate the limit as the previous example. Here, you need to use this property. Since you are sure that the sequence is convergent, which means that all the terms at infinity will be equal to the limit. So L can be replaced by un and un plus 1. So usually, whenever you are trying to find the limit of a recursive sequence, you go to the recursive relation, you replace un by L and un plus 1 also by L. Actually, any u whatever, where this whatever is going to infinity, actually u infinity is L because the sequence is convergent. So plug in L here and plug in L there. Now we will get this relation. So L must satisfy this relation. Cross multiply, L squared minus 7L plus 6 equal to 0. Solving, you will get two values of L. Why do we need to reject one? This is why I said here it's very important to put to put a condition on L. The sequence started with 9 and is bounded below by 6. It cannot go to 1. So 6 is the accepted value. So this sequence is convergent to 6. Another example, consider the sequence un defined by un equals cosine n over n squared plus n, where n is n. By the way, this is an explicit sequence. First, I'm asking you to verify that this inequality holds true. Cosine n over n squared plus 1 lies between minus 1 over n squared plus 1 and between 1 over n squared plus 1 for all n. To find this double inequality, it's very easy, very clear. We have to start with the frame of cosine n. Cosine n as sine n are values which are between minus 1 and 1. Now, dividing all the terms by n squared plus 1, which is a positive quantity. So minus 1 over n squared plus 1 is less than cosine n over n squared plus 1 is less than 1 over n squared plus 1. Deduce the limit of un. Actually, if we wanted to find the limit of this sequence directly, you will face cosine infinity. What is the limit of cosine n as n tends to infinity? By the way, this limit does not exist. Whenever the angle tends to infinity, cosine of the angle or sine of the angle or tangent of the angle will not approach a real number. Imagine the angle is getting bigger and bigger on the trigonometric circle. It's not getting closer and closer to a specific position so that I can get its exact sine or cosine or tangent. So actually, whenever you face cosine infinity or sine infinity or tangent infinity, does not exist. So does not exist over infinity, I don't know. So we need to know this theorem, which we have just studied in the previous slide. Now I find the limit of this, the limit of this, and the limit of this. For sure, we don't know the limit of un. We're trying to find it. But if we find the limit of the extremities, what about the limit of the left extremity? It's what? 0. And the limit of the right extremity is 0. So by the squeeze theorem, since the limits of the two extremities are the same, and un is squeezed between them, then the limit of un is also 0. Thank you for this session.